Welcome to Achieving Wonders with Query Store session. My name is Dennis Torres. I will introduce you to this amazing feature released with SQL Server 2016. I'm a senior software developer from Brazil, working in iSend Software in Malta. iSend Software is a software house which provides software services for many clients such as Bosch, Barclays, RSM, and many others. I'm a Microsoft official trainer and have many Microsoft certifications on data platform, BI, and development. And I'm the Malta Data Platform User Group Leader. Here you see our URL, our site, and you are invited and very welcome to join our site. These are the sponsors. They are the responsible for this event being happening today. And this is our agenda today. Why do we need Query Store? The main question we need to answer. Query Store to the rescue. Query Store writing architecture, reading architecture, schema and configuration. So, why do we need Query Store? Let's talk about some usual problems on production environments. For example, the queries are becoming slower along the time. The queries are sometimes slower and sometimes faster. If I change this, how will this affect my queries? And the main question we usually need to answer is, what has changed? What has changed on our production environment that made our queries become worse? It's easy to check our current query plan. We can check the query plan cache, we can check our current query plan. But what was the old query plan from this query? What changed on the environment? Query Store to the rescue. How Query Store can solve these questions and problems. Let's see what Query Store does. Keep record of every executed query. Keep record of each different plan for every query. So Query Store not only identify the query but identify that the same query is being compiled along the time and getting different plans, and keep track of each plan the query is using along the time. Summarize execution statistics for each plan. So we will not only have the plans the query used, but information about the performance of that plan. And how Query Store works. Let's say the basics about Query Store works. Enabled or disabled on each database. We control Query Store on each database. The information is stored in the database. And the result of all this captured information is that if a query plan changes and the execution statistics become worse, the Query Store history is able to identify it. We are able to get the information from the history and identify, oh, now this query is using this plan, but the previous plan the query was using was way better. This is called query plan regression. When a query changes its plan and the plan becomes worse. We can easily not only identify the query plan regression, but we can also, using Query Store, force the query to use another plan, a better plan. On previous versions of SQL Server, we could only use plan guides to achieve this. From SQL Server 2016, we can use query store to force an older plan. I'm not saying that we will never use plan guides again. There are some situations that we still need to use plan guides, but they are not so usual anymore. We can use query store to force older plans, and we don't need to keep using plan guides all the time. Of course, the best solution is always to identify why a query plan regression happened, why the query plan suffered a regression. But force an older plan is usually a quick solution. And the main question, what has changed? How Query Store can answer this question? And what benefits we get from this answer? The point is, being able to identify change on the environment and the impact of the change can be a great feature for upgrades. Let's say we will upgrade one SQL Server 2014 to SQL Server 2016. How will we be sure that we will not lose on our performance? The queries will not get worse on a new environment, on a new query optimizer and things like that. So we can upgrade the software and keep the old compatibility level. Keep the compatibility level to 2014. Then we enable Query Store, let Query Store capture the information for a while. This will build a baseline, so we will have a baseline of performance for our environment. Then we change the compatibility level to 2016, and some queries may change its plans. Query Optimizer will do its work and improve our queries, but we will be able to identify using Query Store if any plan regression happens, and we can solve plan regressions forcing older plans. This is a great feature for upgrades of SQL Server versions and even any configuration change. If we decide what would happen if I change this configuration, we can check. We can get a baseline from our database, change the configuration, and compare the result after the configuration change. Summarizing this part about upgrades to different versions. We upgrade the server version and keep the old compatibility level. Turn on Query Store to create a baseline. Change the compatibility level. And then fix query regressions, forcing plans. How the Query Store works? How is the writing architecture of Query Store? When a query arrives in SQL Server, the query is compiled. At this moment, Query Store captures the query and stores in the internal tables of Query Store. But at the capture moment, Query Store keeps the information in memory. And the writing to the internal tables is asynchronous, so Query Store will not affect the main work of the server, compiling and executing queries. Then the query is executed and Query Store will capture from the execution the runtime statistics. And again, write the information asynchronously to the disk to not affect the server performance. So we will have information in memory and in the disk. And how is the reading architecture of this information? We have the information. Then we have DMVs, query store DMVs, which merge the information from the in-memory side to the internal tables, and they provide the information to us. We will always have the most current information when we query store DMVs because they merge the information from both places. And the query store schema. What are the tables and DMVs query store use? This is the schema. We have a table to keep track of the queries. Each record on this table represents a query and a set of plan affecting options. Sometimes the same query can be executed with different options that would affect the plan. It becomes a different query for this table. This table is linked to another table with the query test and some context settings. Then, for each query store will keep track of many query plans. All the query plans that query is using. Each time the query is compiled and a new plan is created, a new record on this table is created. One line per plan. And for each plan, query store keep runtime statistics, recording the information about the execution. How is it? Does it record information about every execution? No. This is controlled by an interval, runtime stats interval. The DBI is on control of this interval. It can be set to 5 minutes, 20 minutes. The DBA can control this. So, query store will keep the information in memory and will summarize all the execution information for each interval. And each interval will record one line on the runtime stats table. So we may have one line for every 5 minutes, one line for every 20 minutes. It depends on the DBA configuration. And one line every 20 minutes for each plan, summarizing the statistics of the execution of that plan. These are the internal tables, and we have many exposed views, DMVs. Query test, context settings, store query, and store plan, and the runtime stats view, runtime stats interval, and runtime stats. Besides using these views to retrieve information from query store, we can also use a graphical interface on SSMS. SSMS provides to us a very interesting graphical interface to get information about the queries, top resource consumers, and what resource. We can use duration, CPU time, logical reads, logical writes, and this graphical interface shows information about these queries to us. For each query, it shows the plans the query is using, and the plans the query has used, allow us to force a plan. It's a very, very good interface. Let's see a demonstration about all of this. So let me prepare an environment here. I use master, drop my demo database, stopped. Then I'll create the database again. Create a table called the B store with 3 fields, C1, C2, and C3. I'll create a store procedure, receiving a parameter and making a query over the table, filtering by the C3 field using the parameter. And I will fill the table with many records. I'm using a transaction to become faster, but it will still take 1 minute. Mind that I'm inserting records with many different values on the C3 field, and I'm using different amounts for each different value of the C3 field. This creates a problem. This creates a problem that is usually called parameterization problem or a parameter sniffing problem. Why? Why there is a problem here? Because for some values, for example 0, the best query plan will be 1. For other values, for example 2, the best query plan will be different because the amount of records returned. So the query plan will depend on the value of the parameter, the value used for the parameter. This is called parameterization problem, and query store is able to detect parameterization problem. This is very interesting. We will see an example. So now I will enable query store. Execute the store procedure 20 times. I'm executing 20 times the same procedure. Create an index. Before creating the index, let's check the query store. I have here the database, key store demo, query store. Let's check the top resource consuming queries. My query is the first one, and it's using a plan with a table scan. Okay. I can see the test used for my query here. Okay. I'll create an index over the field C3. The index will help this query, and I will execute the store procedure again 20 times. Okay, check again. The first query is the create index. The second one is our query, and we have 2 query plans for our query plan 8 and query plan 1. The query plan 8 is the new one, is using an index seek and read lookup, while query plan 1 is the table scan. It's easy to note that query plan 8 is way better than query plan 1. But here, using the graphical interface, I can select both query plans and ask to compare the plans. So SSMS shows to me a show plan comparison, highlighting the different operators on the query plan. and I have two property windows for these plans. I can select a common operator, the select in this example, and this window shows to me the values which are different from one plan to another. These are different values among the plans. Let's get an example. Estimated subtree cost using the top plan index 6 0.03. Using the table scan is 0.10. So the index 6 is way better. Okay, let's close this. Get back to our script. Now I'll drop the index. Drop the index. Clear the cache. And execute the stop procedure again. Of course, there is no more index, so the query will start to use the table scan again. Top resource consuming. Is the third now, and here it is. This query is started with plan 1, then executed using plan 8, and then was executed using plan 1 again. This is exactly a situation called query plan regression. The query plan was very good, the query plan 8, and then it became very bad with the query plan 1 again. This is a query plan regression. We can make queries over the query store DMVs to identify the query plan regressions, to identify in our environment which queries has regressed. But from SQL Server 2017 we have a new feature, a new DMV, sysdm-db tuning recommendations. When a query plan regression happens, we get a record on this DMV. Here it is, the record. Type of recommendation is recommended that we force the last good plan. Why? Because the CPU time changed from 0.08 to 1.87. And we have more information about the recommendation. We have a score. If we get many recommendations, we can check the most important recommendation using the score. And we have a state field giving us information about the state of this recommendation. This is a JSON field. JSON fields are a new feature in SQL Server 2017. And we have a details field, which is also a JSON field. Let's read the status information. I can make a cross apply using the function openJSON to open the content of the JSON field and retrieve as data in my query. So I can see here the information. The current state of this recommendation is active. Why it's active? Because automatic tuning option is not enabled. What? Automatic tuning? Yes! That's a new feature in SQL Server 2017. Instead of just getting the recommendations, if we turn on in SQL Server 2017 the automatic tuning, SQL Server will automatically force the older plan when a query plan regression happens. But you may notice for this example, SQL Server is recommending us to force an older plan, and the index of the older plan doesn't exist anymore. So the recommendations are not always perfect. The feature of automatic turning is there, but it's not perfect. I would not keep this feature enabled. I would like to check out the recommendation before implementing one. Let's check now the details field. The details field gives us a very interesting result because the details field is able to give to us the script we can use to force the older plan. We can use this script to force the older plan. This is very interesting. SQL Server is even given to us the instruction we need to execute to force the older plan. That's it. But before forcing the plan, I'll create an extended event session to capture some details here. I'll create this forced plans problem session, capturing query store plan forcing failed event. This event happens when forcing a plan fails. So the session is here. Forced plans problems. Let's start the session. And now I force a query plan. The query plan is forced. Let's check what happens on the graphics. Top resource consuming queries. Let's check our query. Here is our query. You may notice here the plan 8 is checked. It means the plan is forced. We could have used the interface to force the plan, or the instruction, like we did, and the plan is forced. Let's execute the stop procedure again. Of course it will not work. We don't have the index anymore. It will keep using table scan. And we have the forced plans problem. We can check the ring buffer, and we already have information on the ring buffer about failures of forced plans. Here it's already illustrating to us that a forced plan failed. And it's specifying why, because the index on the plan doesn't exist. So we can capture using extended events when a forced plan fails to execute. We can also get information about the recommendation. Let's see the status of the recommendation. Now that I forced the plan, the current state of the recommendation is expired. It's not a valid recommendation anymore. Why? Because the plan was forced by the user. We executed the instruction to force the plan. So the recommendation is expired. This is the current state of the recommendation. And we can use some queries over the query store DMVs to get the list of forced plans from query store. Now I have only one forced plan, but this list is showing to us the failure reason of our plan, why our plan failed. So mind that we have more than a single way to check the failure of forced plans. We can use the extended event that I showed to you, and we can use this query to check what was the reason of the last failure. Let me create the index again, execute the stop procedure again, and now the forced plan is working fine. An index seek. The problem is that from the query of query store DMVs, we still see the reason of the last failure. This query doesn't tell us that the plan is already executing fine. We will still see the reason of the last failure. So we may need, on some situations, to carefully analyze the result and even check both, check the queries and check extended event. So we just saw a forced plan working, that's fine. Now I will execute the stop procedure many times. You may notice that I'm changing the value of the parameter 0, 2, 0, 2. I'll be executing this stop procedure many times. I already explained that this stop procedure suffers from parameterization problems. The perfect plan for the parameter 0 is 1. 0 can use the index seek because it brings a very small amount of records. But for the value 2, the index seek is terrible because there is a grid lookup on that plan. And the amount of records is huge. So this query is terrible for the value 2. This creates an interesting result on the statistics information about execution. What will happen on the statistics information? What will happen is that the statistics about the query will vary a lot. The query will be very fast when executed for one value, for the value 0, and will be very slow when executed for the other value, the value 2. So the execution will vary a lot. To identify this, we have a new graph here called queries with high variation. We can check this graph, and our query will be somewhere here. Here is our query on third position. Let me change the variation. It's a different mathematical calculation. I prefer to check the standard deviation of the query, and we notice that for the standard deviation of our query is the first one. It's a very high standard deviation, and we notice here the plans and a deviation of the execution. We notice a deviation of the execution. The plan 17 is the same than the plan 8, but 17 gets a recommendation of a different index. gets a missing index recommendation. Very interesting. So the point is, using this graph, queries with high variation, we can identify queries that are suffering from parameterization problems. Before SQL Server 2016, we could only test query by query. The only way to check if the query has this problem it was to check query by query. Now, with this capture of baseline and statistics information by the query store, we can get this information from the query store tables. In fact, this graph, queries with high variation, was created only in SQL Server 2017, not 16. But from the 2016, we could read the information from the query store DMVs. For example, I even wrote an article about this. We can create a function. Here I am creating a function. Queries with high parameterization problems. To capture statistics information of the last plan used by the query. Filtering to get only parameterized queries and removing system queries. Then I can make a select over this function, order by standard deviation CPU time desk, and here we get the query which is suffering of parameterization problems and the standard deviation of the CPU time consumption. So we can, using query store, identify queries with parameterization problem. The DMVs of query store are very powerful. The information on these DMVs are great. They keep information about duration, CPU time, logical reads, logical write, physical reads, physical write. It's all here. It's all here. And for each measure it has the minimum value, the average value, the standard deviation, because each record is an interval of time of the execution. So it gets a range of values during this interval. It's all here. What can we do with all this information? This is a baseline, a performance baseline for our environment. We can capture all this and, for example, analyze using Power BI. This dashboard is reading the information from SQL Server, and we can check, for example, one of the tables has information. This DMV was created on SQL Server 2017 and has the information about weight stats. Weight stats used for each query. This is absolutely great. We can identify which weight stats are hurting our server on each day of the week, on each hour of the day. We can identify which weight stats are hurting our server. We can create a line of the progress of each weight stats along the time. So we can analyze the query store information using Power BI to create a dashboard, a performance dashboard for our SQL Server. No problem. This dashboard, this Power BI dashboard, is a template that I published in GitHub as a starting point to create more powerful dashboards. So let's get back to our slides. Let's talk about query store configuration. Turning on the query store, we have two important configurations: operation mode that can be set to read-write, read-only, or off. Read-write, query store is on. Off, query store is off. But what's read-only? The read-only means that query store is providing the DMVs, the data is there, but query store is not capturing anything. Sometimes we would like to turn on query store off and keep the data there, but sometimes this happens by mistakes on the configuration. We will see this. And query store capture mode is different than the operation mode. Query store capture mode is for capturing the queries. We can capture all the queries. We can let query store decide which queries it will capture. It depends of the performance of the query. It will capture the biggest queries or none. We can turn off the capture and only work with the queries already captured by query store. Query store will continue capturing performance statistics but not new queries. Writing and collection. We have the data flush interval in minutes. What this means? Query store keeps information in memory. What interval query store will use to flush the information to the disk? So this configuration sets this interval, data flush interval. We can use smaller values, but smaller values may affect the performance of the server, or we can use longer values, but in this case we may lose information if our server shuts down unexpectedly. Statistics collection interval. This is the collection for the runtime statistics, which interval will be used to summarize the runtime statistics in records on the runtime statistics DMV. The value used for the collection interval may create better statistics or worse statistics, changing the meaning and the precision of the information stored by query store. Size and cleanup. Size-based cleanup mode, auto or off. Query store can make a cleanup when it achieves a size limit, and we have a size limit here, max size. And the stale query threshold, for how long days we would like to keep our queries in query store, and after these days, if the query is not being executed anymore, clean this query from the query store history. So using these configurations, we can control the size of the information captured by query store. And you may notice that a bad configuration here may lead to a situation where we don't have space anymore to capture queries because we have a max size. So if this happens, the operation mode of query store automatically changes to read only. This is the query store configuration. Its own database properties. We can see the database properties and this configuration that I just talked about. And an example to set these configurations using the SQL. Many of these configurations are on this example. And about controlling query store data using the SQL, we can flush the data to disk at any moment using sp query store flush db, and clear the query store information, alter database, the name of the database, or Current is a new feature on SQL Saturday 2017. Set query store clear to clear the query store data. Some query store behaviors. When the server is shutting down, what happens with query store? Query store saves the data when the server is shut down, unless the server receives a shutdown with no wait. In this case, query store will lose the data. Since query store will save the data when the shutdown is requested, this may take some time. If you need to shut down the server with not having this delay, you can enable the trace flag 7745. This changes this default behavior, and query store will not save the data when the server is shut down. It will lose the data. And when the server is starting, query store tables are restarted synchronously, and part of these tables are loaded to the memory. But if you enable trace flag 7752, this behavior is changed and query store is started asynchronously. This will improve the start time of the server. Optimize for ad hoc workloads. Do you know what is it? Sometimes we get an ad hoc query, a query that is executed once and never executed again over our server. This can happen. If query store keeps recording these queries, the query store information will be huge. So we have a configuration at server level, and this configuration is not totally linked to query store, called optimize for ad hoc workload. It's a good practice to enable this configuration for environments using query store. This avoids the ad hoc queries to be monitored. How this affects query store? It's because when the query is executed for the first time, the query plan of this query is not stored in the query plan cache. The query plan cache only stores a stub, a proxy for this plan. The plan is not stored in the cache. So, as a consequence, query store doesn't capture this query. Only on the second time this query arrives to the server, then the query plan is stored in the plan cache, and query store will capture this plan. So query store tables will be smaller and cleaner. Extended events. I illustrated one extended event to check forced plans, but query store has a total of 92 events. We can control many details about query store operation and check many possible problems about query store operation. You have a total of 92 extended events to check. So here you have the link of the query store dashboard, Power BI query store dashboard on GitHub. An article I wrote for Simple Talk about query store parameterization, identifying parameterization problems with query store, and my contacts. You will be able to find a recording of this session on my YouTube channel. Thank you very much for your presence.